Hello, and welcome back. This is Unit 5 in AP Calculus. This unit is all about applications of the derivative. Today I want to focus on graphs of functions and derivatives. So let's take a look. We'll start with this question here. Consider the graph of f shown below. At each of the labeled x values, answer each of the following for f prime and justify. So this is, it says, and justify. Oh boy, typos, right? All right, so pause the video and see if you can answer questions. Remember, this is the graph of f, and we're asking about f prime at each of these locations. All right, so at point A, first of all, is f prime increasing, or is f prime positive, negative, or neither? So f prime is positive at A because because f is increasing. So f prime is positive whenever the graph of f is increasing. F prime of x is decreasing because f is concave down. So can you see the concave down shape? All right. Let's about letter B. F prime at B must also be positive. Again, because f is increasing. But unlike at A, f prime is increasing. F prime is increasing because f is concave up. All right, what about letter C? Well, we can see that f prime must be negative because we're decreasing. Let's see here. Because f is decreasing. And we're also concave down. All right, so we're concave down. So f prime, if we're concave down, f double prime is negative, which means f prime is decreasing. It's getting more negative. Lastly, at D, f prime is negative because f is decreasing. And f prime is increasing because we're concave up. And I say concave up at that point location. All right, let's take a look at practice 7.2. Suppose the function f is differentiable on the closed interval from 0 to 5. If f of 0 equals 4 and f of 5 equals 19, I would like you to answer each of these three questions. So pause the video for a minute, please. And I think that's it. It was just those three. Yeah, pause the video and give it a try. All right, can you conclude that f of 3 is equal to 15? Well, no, I don't have any information about that, right? I know f of 0 is 4 and f of 5 is 19, so no. We cannot conclude this. Can I conclude that f of x equals 14 has at least one solution on the open interval from 0 to 5? Well, yeah, I can conclude that because, see, f is differentiable, right? Since f is differentiable, that implies that f is continuous because to be differentiable, you have to be both continuous and smooth. So f is continuous on the closed interval from 0 to 5, right? And we know that f of 0 is less than 14, and we know that f of 5 is more than 14. So the reason why I know that must happen is called the intermediate value theorem, the IVT. We know that f of x equals 14 for at least one value of x on that open interval. That is guaranteed. Can you conclude that f prime of x is equal to 3 has at least one solution on the interval from 0 to 5? Well, let's We're talking about the derivative, so let's look at the average rate of change. That's what we would be able to figure out. So that'd be f of 5 minus f of 0 over 5 minus 0. Well, f of 5 is 19, and f of 0 is 4. So that's 15 over 5. That's 3. So since f is differentiable on that interval, we know that f prime of x is equal to 3 for some value on the open interval from 0 to 5 by the MVT, the mean value theorem. So the intermediate value theorem, intermediate meaning in between, the intermediate value theorem guarantees that f equals that y value somewhere. The mean value theorem guarantees that f prime equals the value of the slope of the secant line somewhere. So let's do practice 7.3. Consider the graph of f prime of x, the derivative of a twice differentiable function f. Okay, so that's f prime, and we know f prime f is twice differentiable. So pause the video, and let's see here. I think we just have these 3 questions here, right? Yeah, just these 3 questions. Give it your best shot. On the interval from -3 to 3, where does f have a relative max? Well, that's not too bad. We know what to say there. X equals 1, right? At x equals 1, f has a relative maximum because f prime of x changes from positive to negative at x equals 1. From -3 to 3, on what intervals is f concave up or down? Justify. So we know that f is concave up on the interval from -3 to, you might say -3 to -2, and then -2 to 0, right? So I'll say that. -2 to 0. How do I know that? How do I know that? Well, because f prime is increasing on those intervals. Okay, well, how do I know? Then let's answer the next question. How do I know that where f is concave down? Well, f is concave down on 0. Looks like 0 to 2, and then again from 2 to 3. Because f prime is decreasing on those intervals. So remember, the definition of concavity says that concave up means the derivative is increasing. So it's just simply asking us, when is f prime increasing, when is f prime decreasing? These points here are somewhat contentious. Can we just have said it's increasing from -3 to 0? Can we just say it's decreasing from 3 to 3? Yeah, we can, and that answer is acceptable, and certainly AP grade is accepted. I just, I say that, at that moment it wasn't increasing or decreasing at all because of that horizontal tangent line. But that's just for me. Okay, so at what x values does f have an inflection point? F has an inflection point where f prime changes from increasing to decreasing or decreasing to increasing. So that is going to be at x equals 0. F has an inflection point or point of inflection because f prime changes from increasing to, not positive, sorry, I can't say that, from increasing to decreasing. All right, so on 7.4 you have A, B, C, D, and then E right then here. On what intervals is f decreasing? So try and answer all of those if you can. All right, let's see how we did. We're looking at the interval -5 to 5. All right, and this is a graph of f prime. So does f have a relative max, minimum, or neither at x equals -4? Well, this is a graph of f prime, so we can say that f has a relative minimum at x equals -4 because f prime changes from negative to positive. Is f continuous at x equals 0? Is f continuous there? Well, yeah, definitely. How do I know? Yes, because f prime of 0, let me write that better. Hold on. F prime of 0 is defined, and differentiability implies continuity. Is f differentiable at x equals 0? Well, this is kind of a gotcha kind of question that a lot of people miss. Yes, f is differentiable. It's not twice differentiable. The derivative is not differentiable there. That's a shortcut. But that's f prime. F is differentiable at x equals 0 if f prime is continuous there. So is f differentiable at x equals 0? Yes. Because f prime of 0 is defined. You see? I mean, it's totally differentiable there because it has a value. In fact, f prime of x is equal, or f prime of 0 is equal to 4. We know its value. For what x values does f have an inflection point? Okay, well, f has an inflection point f has inflection points at x equals 0, 2, and 3 because f prime changes from increasing to decreasing or decreasing to increasing. Over the closed interval -5 to 5, for what intervals is f decreasing? Well, only from -5 to -4 because f prime is less than 0. That's it. All right, let's see what we have on this next one. We have, looks like, well, a few questions here. So give it your best shot. There is this question R down at the bottom, so you can pause the video later and get to that if you want. All right, so pause it and give it a try. All right, practice 7.5. A small block of ice is placed on a city street. The function c of t equals t minus 3 cubed minus t squared plus t plus 27 models the temperature of the ice in degrees Celsius from 7 a.m. to 12 p.m. During which hours is the temperature decreasing? Well, let's take the derivative. And then minus 2t plus 1. So we need to figure out when is this negative. Well, we can expand that, right? That'd be t squared minus 6t plus 9 minus 2t plus 1. So that'll be 3t squared negative 20t and then plus 28. All right, now I'm not sure if this is factorable or not, but we could try. Let's see here. That would be 24 plus 6 would be 84. All right, so we can, let's see here. Let me bring that over here. We can factor that as, so this is c prime again of t. And I get 3t minus 14 and t minus 2. So we see that it's going to be equal to 0. So c prime of, looks like 14 over 3 and c prime of 2 equals 0. So when is the temperature decreasing? Well, that would be when the derivative is negative. You can see this derivative is a parabola, right? It's a parabola opening upwards, so it's not that hard to imagine on the number line that it's intersecting at 2. And then let's see here, 19 over 3 is, let's see here, 5. 14 over 3 is just a little less than 5, right? 4 and 2/3. So 4 and 2/3. And we're going to be, if you put a 0 in here, you'll get a big positive number, and then it'll be positive here and negative. So it's got to be between t equals 2 and t equals 19/3 hours. So what is that, like 9 a.m. to, well, let's see, is this 19/3 actually, part of it? Well, it is actually, because that's 11 and 2/3, so 11:40. We could get really exact here and say that it's from 9 a.m. to 11:40 a.m. But, and we know this because c prime is negative. But I'm not going to worry about getting too descriptive there. All right, during which time was the temperature increasing at an increasing rate? Increasing at an increasing rate. Well, we know that the temperature was increasing from, let's see here. It was increasing from 0 to 2, and then it's increasing from 4 and 2/3 to 12, or 5, because that's the last hour, right? Well, let's find the second derivative. And I'll use this expanded version. 6t minus 20. So when does that equal 0? Let's see here. At 20 over 6. Or 10/3. And you can see that the shape of this second derivative is a line with the y-intercept at negative 20. So it's going to start negative and then go to positive. So this is where it's concave up. This is where the temperature is increasing, right? Sorry, this is where it's concave up. This is where the rate of change is increasing. So we know that on the interval from 19/3, whoops, that's 19/3 to, let's see here, 5, right? We know that c prime of t is positive, and c double prime of t is positive. So c is increasing at an increasing rate. It is increasing faster and faster. What is the absolute maximum temperature from 7 to 12? Well, to figure that out, we would need to evaluate c of 0, because t equals 7 is, t equals 0 is the time at 7 a.m. So c of 0. C of 2, that's another critical number, right? C of 19/3. And C of 5. Which, if we have a calculator, is not that hard. But I will say that when you look at our number line, we can see that this is a local maximum, 4 and 2/3. A local minimum. The graph is going down and then up because the derivative goes from negative to positive. So there's no way. This is the smallest value in a neighborhood around us. There's no way that's the maximum. So let's just evaluate c of 0. That'd be a negative 27 plus 27. That's 0. C of 2. That would be 1 cubed is 1. So negative 1, sorry. Minus 4 is a negative 5. Plus 2 is a negative 3. Plus 27 is 24. And then c of 5 would be 2 cubed is 8. 8 minus 25 is a negative 17. Plus 5 is a negative 12. Plus 27 is what did we say, negative 12 or negative 15? We said 8. I'll have to write it out, actually. 8 minus 25 plus 5 plus 27. So that's 32. That's 7. So 15. So it looks like C of 2 is the winner by the candidates test. And if I'm not going to show how I did that, how you evaluate C of was 14 over 3, you need to explain why you know it's not an absolute maximum by explaining that it's a relative min. The function R, the rate of evaporation of the pool, is a function of the pool's temperature. Express the rate of change in the rate of evaporation. So, a small block of ice is placed on the city streets. Okay, models the temperature of the ice in degrees Celsius. Okay, so the last question, it did have a bit of an error to retype it. It said the evaporation of the pool, but it's really the puddle of water. So the function R, the rate of the evaporation of the puddle of water formed by the melted ice, is a function of the ice's temperature. So the colder the ice is, probably the slower the water will evaporate, but the water that's melted already from it. So we're going to express the rate of change in the rate of evaporation. So what we know is that R is a function of the temperature. So R is a function of the temperature, which is C of t. So the rate of change of this function, the d dt, would equal R prime of C of t times C prime of t. And you could go ahead and now plug some stuff in, but understand we don't know R, so we just say R prime of, and then we can replace it with, this function, which I'm going to just cheat here. Put it there. And then I will finish that off. So it's R prime of that times 3t minus 3 squared times the derivative of the inside, which is just 1, minus 2t plus 1. And that's it. All right, let's take a look at another problem. We have a table, looks like here. Various values of the velocity in meters per second of a particle A, v sub A. So we have particle A with velocity v sub A, and another particle B has velocity v sub B. Makes sense, right? Are shown in the table below for various times t seconds. V sub A and v sub B are differentiable functions. All right, so let's see if we can't. How many practice problems we got here? I think we have probably quite a few on this one. We got a ton. So let's just take it a couple of times. So do A and B first, and we'll move on. All right, so explain why there must be at least one time on the interval from t of 2 to 12 where v prime of A of t equals 0. Well, let's see here. At least one time. Well, let's see here. V sub A of 2 is equal to 6. And V sub A of 8 is also equal to 6. And since they're differentiable, so also continuous, so we can say by Rolle's theorem, and we could also use the mean value theorem if we showed that the average rate of change there is 0, which it certainly is. By Rolle's theorem, v prime of A of t equals 0 somewhere on the interval from 2 to 12. Now, there's lots of different ways you could say that, but make sure you understand that we're not saying that v prime of A equals 0 everywhere from 2 to 12. We're saying just one time at least. All right. On letter B, we have explained why there is at least one time where VB equals 0. So notice that this is not saying that V prime of B. This is saying that V of B equals 0. Well, that I'm going to use something different. I'm going to say v sub b of 8 is equal to 3. V sub b of 9 is equal to negative 1. V sub b is differentiable, and so therefore V sub b is continuous. And this is the mean value theorem. By the mean value theorem, V sub b of t equals 0 somewhere, or at least once, on the interval from 8 to 9. The functions s sub b of t is a I'm gonna have you do C and D now. The functions s sub b of t is a position function for particle b that has velocity v of b as its function. Is it possible that s sub b is concave down? Explain. All right, so let me have you try that. Now what I'm going to do is I'm just going to take this table here. You know, usually when you work these problems on paper, you can see everything at once. So let's just paste that right here. Okay. All right, so give that one a try. Try C and D. Pause the video. Okay. Is it possible that S sub B is concave down? Okay, on that interval from t to 12. Well, if S sub B is concave down, what does that mean? Concave down means that S prime of B, that the definition of concavity means that S prime of B, S prime B, is decreasing, right? To be concave down, S sub prime of B must be decreasing. Well, what is S prime of B? Well, S prime of B is equal to V sub B of T. Well, is it decreasing? Yeah, it is decreasing. You know, do I know it's concave down everywhere? Maybe it increased for a little while. I don't know. But because the table shows decreasing values of V sub B of T, it is possible that S of T is concave down. There we go. Is it possible that V sub B is concave down on... Is it possible that V sub B is concave down? Ooh, a little different. Is it possible that the derivative of S? Okay, well then, in order for that to be the case, then we would need the acceleration. We would need the derivative of VB to be decreasing. Well, let's take a look. I'm going to find the average rate of change. Of V sub B. Let's do it from 5 to 2. That would be 8 minus 10 over 5 minus 2. That is a negative 2 over 3. Let's do the average rate of change on the next interval. This was average rate of change from 2 to 5. Let's do 5 to 8. That would be 3 minus 8 over 8 minus 5. That's a negative 5 over 2. Let's do the next one. That would be a negative 1 minus 3 over 9 minus 8. That's a negative 4, right? Negative 4 over 1. And then lastly, we have negative 2 minus a negative 1 over 12 minus 9. That is plus a positive, so that's a negative 1 over 3. Ooh. So what we see here is that the rate of change, so we know that the average rate of change seems to be decreasing, right, for a little while, but then the average rate of change changes again. So we know somewhere on the interval, by the mean value theorem, we know somewhere on the interval from 8 to 9, the derivative is negative 4. And we know somewhere in the interval from 9 to 12, the derivative is only negative a third, which means that it would actually be increasing. So the derivative is increasing from 9 to somewhere on the interval from 8 to 12. And I don't have enough room to write all that down, but that's the idea. So the idea is no. Maybe from, 2 to 8, but I can't say it from 2 to 12. I cannot guarantee. I guarantee it's not. All right. Letter E says, for the interval from 2 to 12, must there be a time when V sub A obtain a maximum value on this interval? Well, the extreme value theorem says that if a function f is continuous on a closed interval, it must obtain a maximum. May happen multiple times, but it's going to be a max value. So, because V sub A is differentiable, and therefore continuous on the interval from 2 to 12, by the extreme value theorem, we got the MVT, the IVT, and the EVT. By the extreme value theorem, V of A obtains a max on this interval somewhere. We know it must. That is guaranteed by the extreme value theorem. All right, practice 7.7. If you would pause the video and try that, please. All right, consider the graph of f prime. This is the graph of f prime, right? What is f prime of negative 3? Okay. Well, we could kind of guess. It definitely looks to be 2, but they gave us these points, so maybe we should actually do a little bit of linear analysis here. We should probably do, not linear, but linear extrapolation. Let's see if we can't figure that out. What's the slope of this line? We can see that the slope of this line is equal to up 3 over 3, right? So 1. We went over 1, 2, 3 to get to this point, and we went up 1, 2, 3. So because of that, I know that this is negative 4, 1. This is negative 3, 2. So it's got to be 2. Okay. What is f double prime of 3? Well, if this is f prime, this is a graph of f prime, well then f double prime is the slope of f prime, which is just 1. We just figured that out. If g of x equals f of the natural log of x, find g prime of 1. Okay. G prime of x then is f prime of the natural log of x times the derivative of the natural log of x. So g prime of 1 is f prime of the natural log of 1 times 1 over 1. The natural log of 1 is 0. Remember, log of anything to the 0 power is 1, so the natural log of 1 must be 0. And so this is asking for f prime of 0, which is 1. All right, let's take a look at practice 7.8. Consider this graph here with a domain from negative 3 to 3. For what values from that interval, negative 3 to 3, is f increasing? Do A and B here. And so also find what has a relative max. F is increasing on the interval from negative 3 to negative 2, and 0 to 2, and 2 to 3, because f prime is greater than 0. For what values of x on the interval from negative 3 to 3 does f have a relative maximum? F has a relative max at x equals negative 2, because that's the only point where f prime changes from positive to negative. For what values of x, let's bring this graph down. Let's go ahead and let's copy that, right? So we can hopefully you got all that, right? I'm going to move it down here. Okay, for what values of x on the interval from negative 3 to 3 is it concave down? Answer that. All right, well, f is concave down on the interval from negative 3 to negative 1, and on the interval from 1 to 2, because f prime is decreasing. That's the definition of concavity. Concave down is the definition of being concave down is to have the derivative decreasing. So when does it have an inflection point? It must be at x equals negative 1 and x equals 1 and x equals 2, because f prime changes from increasing to decreasing, or decreasing to increasing. Suppose that f of negative 3 is 0. Sketch a possible graph. So let's do that. 1, 2, 3. All right, we need to be increasing and concave down until we reach a relative max at negative 2. We'll continue being concave down till we hit negative 1, in which case we will switch to being concave up, and we'll reach a relative min at 0, where we switch to increasing. Notice we're decreasing all the way from negative 2 to 0. We're going to be increasing the rest of the way, but we're going to be concave up here. We're going to switch to concave down till we get to negative, till we get to 2. We're going to flatten out, make a horizontal tangent line because the derivative is 0. But we're not going to stop increasing. We're going to switch back to concave up and keep going up. All right, that is the end of this lesson, and that's the end of this unit. Next unit, we have more applications of derivatives. We'll be looking at some greater applications like optimization problems and some more particle motion problems. Just lots more to do. So look forward to that. Take care.